Right now, as you're listening to this, something unprecedented is unfolding in the depths of our solar system. On July 1st, 2025, an automated telescope in Chile's Atacama Desert captured a single frame that would rewrite our understanding of what travels between the stars. Hidden within that image was an object so extraordinary, so statistically impossible, that it challenges everything we thought we knew about our cosmic neighborhood. This video examines published scientific research and historical records for educational purposes. Interpretations are attributed to their respective sources and the scientific community's ongoing analysis. The object in question bears the designation 3IATLAS, marking it as only the third confirmed visitor from beyond our solar system. But unlike its predecessors, this wanderer carries characteristics that have left astronomers questioning the very nature of interstellar space. What they've discovered goes far beyond a simple comet passing through our cosmic backyard. The measurements, the trajectories, the timing of its arrival all point to something that shouldn't exist according to our current models of how the universe works. As we speak, this mysterious traveller is making its closest approach to Mars, offering humanity an unprecedented opportunity to study an object that may hold answers to questions we've barely learned to ask. But the more we observe, the more puzzling it becomes. The data streaming back from our most sophisticated instruments paints a picture of an interstellar visitor that defies conventional explanation. To understand why 3IATLAS has captured the attention of astronomers worldwide, we need to examine what makes it so remarkably different from anything we've seen before. When the ATLAS survey telescope first detected this object, it appeared as nothing more than a faint smudge moving against the stellar background. But as observations accumulated and trajectories were calculated, a stunning reality emerged. Dr. Avi Loeb from Harvard University has classified 7 distinct anomalies that set this object apart from known natural phenomena. The first and perhaps most striking concerns its sheer size and mass. According to current models of interstellar object populations, 3IATLAS is anomalously massive, outweighing the previous interstellar visitors by 3 to 5 orders of magnitude. The implications of this disparity are profound and deeply unsettling from a statistical standpoint. Consider this carefully. Given the limited reservoir of heavy elements available during planetary formation, mathematical models suggest we should have discovered approximately 100,000 smaller interstellar objects before encountering something of this magnitude. Yet we've only detected 2 previous visitors from beyond our solar system. The probability of discovering such a massive object so early in our catalogue of interstellar visitors approaches statistical impossibility. The mass calculations are equally remarkable. Current estimates place 3IATLAS at over 33 billion tons, requiring a solid nucleus larger than 5 kilometers in diameter. For perspective, this makes it potentially larger than many asteroids in our own solar system's main belt. When researchers first calculated these numbers, many assumed there had been measurement errors. But repeated observations from multiple independent sources confirmed the extraordinary dimensions. The Hubble Space Telescope has provided the most precise measurements to date, constraining the diameter to somewhere between 440 meters and 5.6 kilometers. Even at the conservative lower estimate, this represents an object of unprecedented scale for an interstellar visitor. The upper limit would make it a genuine mountain hurtling through space at velocities exceeding 130,000 miles per hour. But size alone doesn't account for the growing unease in the astronomical community. The chemical composition revealed through spectroscopic analysis tells an equally puzzling story. When the European Very Large Telescope turned its spectrograph toward 3IATLAS, the results defied expectations in ways that continue to perplex researchers. The object's spectrum reveals the presence of nickel and iron atoms in quantities and ratios unlike anything observed in previous comets, whether from our solar system or interstellar space. The significance of this discovery cannot be overstated. Nickel and iron are refractory metals that typically remain locked in solid form at the surface temperatures experienced by comets at such distances from the Sun. Their presence in the gaseous envelope surrounding 3IATLAS suggests either unprecedented heating mechanisms or compositional characteristics that don't align with our understanding of natural comet formation. The previous interstellar visitor, 2I/Borisov, displayed nickel and iron ratios consistent with solar system comets, making it appear familiar despite its exotic origin. 3I/ATLAS breaks this pattern entirely, exhibiting metal abundances that suggest formation under conditions radically different from any known stellar environment. The James Webb Space Telescope has added another layer to this chemical mystery. Its infrared spectrograph detected significant outgassing activity, with the object releasing approximately 150 kilograms of material per second as it approaches our Sun. This massive rate of material loss would typically produce detectable changes in trajectory due to the rocket effect of expelled gases. Yet 3I/ATLAS continues to follow a purely gravitational path with no measurable deviation. This absence of non-gravitational acceleration, despite substantial outgassing, represents a fundamental puzzle. Natural comets experiencing such material loss rates invariably show trajectory changes as expelled gases create thrust effects. The fact that 3I/ATLAS maintains perfect gravitational motion while losing hundreds of pounds of material every second challenges basic principles of celestial mechanics. Dr. Loeb has noted that this combination of massive outgassing with zero trajectory deviation suggests either extraordinary mass that makes such effects negligible or physical processes we don't yet understand. The implications extend beyond simple curiosity about an unusual comet. Perhaps the most thought-provoking aspect of 3I/ATLAS involves not what it is, but where it's going. The object's orbital trajectory reveals alignments so precise that they challenge our understanding of random cosmic motion. These aren't subtle mathematical curiosities buried in complex calculations. They're obvious, striking patterns that jump out of the data. The object approaches our solar system on a retrograde orbit, moving opposite to the direction of planetary motion. This trajectory lies within 5 degrees of the ecliptic plane, the relatively flat disk containing Earth's orbit around the Sun. For a randomly oriented object arriving from interstellar space, the probability of such precise alignment is approximately 0.2%, or roughly 1 chance in 500. But the alignments don't stop there. 3I/ATLAS will make remarkably close approaches to Venus, Mars, and Jupiter during its passage through our solar system. The combined probability of such multiple planetary encounters occurring by chance is less than 0.005%. We're looking at odds of approximately 1 in 20,000 against such precise navigation occurring naturally. Some researchers have noted that this retrograde trajectory, aligned with the ecliptic plane, would provide tactical advantages for any object conducting reconnaissance of our solar system. The orbital configuration allows access to multiple planets, while remaining difficult to intercept or predict, since retrograde motion makes long-term trajectory forecasting more challenging. The timing adds another layer of statistical improbability. 3I/ATLAS will reach its closest approach to the Sun on October 29th, 2025, when Earth will be positioned on the opposite side of our star. This geometry makes terrestrial observations extremely difficult during the object's most active phase, when solar heating reaches maximum intensity and any technological systems would have access to abundant power. A technological probe aware of observers eager to study it from Earth might favour precisely these circumstances. The configuration provides maximum energy availability while maintaining concealment from our most powerful telescopes. Whether this represents intentional strategy or remarkable coincidence remains an open question that the astronomical community continues to debate. Today marks a pivotal moment in our understanding of this mysterious visitor. As 3I/ATLAS makes its closest approach to Mars at a distance of 29 million kilometers, an unprecedented observational campaign is underway. Multiple spacecraft positioned around the red planet have turned their instruments toward this interstellar traveler, providing humanity's best opportunity to study such an object during its active phase. NASA's Mars Reconnaissance Orbiter, equipped with the high-resolution imaging experiment, should capture images with spatial resolution of 30 kilometers per pixel. These will represent the highest resolution photographs of 3I/ATLAS obtained to date, potentially revealing structural details invisible from Earth-based telescopes. The European Space Agency's Mars Express and ExoMars Trace Gas Orbiter are contributing their own specialized instruments to this coordinated effort. The CASIS camera system and NOMAD spectrometer aboard the Trace Gas Orbiter will analyze the composition of gases surrounding the object, while Mars Express deploys its high-resolution stereo camera for additional imaging perspectives. This represents more than routine scientific observation. The data collected during these crucial hours may provide definitive answers about the nature of 3I/ATLAS, or raise even more perplexing questions about what we're witnessing. The significance of this Mars encounter extends beyond immediate scientific curiosity. If 3I/ATLAS exhibits any unusual behavior during this close approach, if it shows signs of maneuverability or releases additional objects, the implications would be profound. The spacecraft positioned around Mars serve as humanity's early warning system, our first line of detection for any anomalous activity. However, despite the scientific importance of these observations, an unusual delay has occurred in the public release of data. Both NASA and the European Space Agency have yet to publish the images and spectroscopic results from their Mars missions, despite the encounter occurring as scheduled. This delay has generated speculation about the sensitivity of the findings or the need for extensive analysis before public disclosure. But what happens next may prove even more significant than what we observe today. As 3I/ATLAS continues toward its appointment with our Sun, it carries implications that extend far beyond a single astronomical object. But the mysteries surrounding 3I/ATLAS extend far beyond its current passage through our solar system. Recent analysis has uncovered a connection that reaches back nearly half a century, linking this interstellar visitor to one of the most famous unsolved mysteries in the history of radio astronomy. On August 15th, 1977, Ohio State University's Big Ear telescope detected something extraordinary. For exactly 72 seconds, a powerful radio transmission blazed across the cosmos, so intense and precisely structured that astronomer Jerry Amon scribbled "Wow" in the margin of the computer printout. This became known as the wow signal, and despite decades of investigation, no natural explanation has ever been found. The signal originated from a region of space that appeared empty, devoid of any known astronomical objects capable of producing such a transmission. Its characteristics suggested artificial origin, yet it never repeated despite extensive monitoring of the same coordinates. For nearly 50 years, the wow signal has stood as astronomy's greatest enigma. Now, Harvard's Dr. Avi Loeb has identified a remarkable correlation. When researchers traced 3I/ATLAS backward through its galactic trajectory, they discovered that in 1977, this object would have been positioned within approximately 4 degrees of the wow signal's origin point. The probability of such alignment occurring by random chance measures at roughly 0.6%. This statistical connection becomes more intriguing when we consider the power requirements. If the signal originated from 3IATLAS at its 1977 distance, the transmission would have required between 0.5 and 2 gigawatts of power. For perspective, this equals the continuous output of a nuclear power plant focused into a precise radio beam aimed toward Earth. The timing adds another layer of significance. Just 5 days after the WOW signal's detection, NASA launched Voyager 2 on humanity's grandest journey to the outer planets and beyond. 2 extraordinary events within a single week. The reception of what might be the first confirmed message from another intelligence, followed by our own species' most ambitious attempt to explore the cosmos. Some researchers suggest this sequence may represent more than historical coincidence. The correlation raises questions about whether 3I/ATLAS might have been observing our technological development, timing its current approach to coincide with our increased capability to detect and study interstellar objects. The discovery of 3I/ATLAS arrives at a pivotal moment in human astronomical capability. Until recently, finding interstellar objects required extraordinary luck and persistent observation. The previous 2 visitors, 1I/Oumuamua and 2I/Borisov, were detected almost by accident during routine sky surveys. That situation has changed dramatically with the completion of the Vera C. Rubin Observatory in Chile. This revolutionary facility represents a quantum leap in our ability to monitor the cosmos. Where previous surveys discovered approximately 20,000 new asteroids per year, the Rubin Observatory found 2,104 new objects in just its first 10 hours of operation. This 1,000-fold increase in detection capability suggests we may be entering an era of regular interstellar visitor discoveries. What once seemed like rare cosmic curiosities may prove to be common travelers in the space between stars. The implications extend far beyond simple cataloguing of celestial objects. If interstellar objects pass through our solar system regularly, as the new detection rates suggest, then 3I/ATLAS may not represent an isolated phenomenon. Instead, it could be our first detailed look at a population of travelers that has been crossing our cosmic neighborhood undetected for millennia. The enhanced observational capabilities also mean that future interstellar visitors will be discovered much earlier in their approach, providing extended opportunities for study. Unlike 3I/ATLAS, which was found only months before its closest solar approach, future objects might be tracked for years as they journey through the outer reaches of our solar system. This extended observation time could prove crucial for understanding the true nature of these visitors. The brief glimpses we've had of previous interstellar objects have left fundamental questions unanswered. With more time and better instruments, we may finally determine whether these travelers represent purely natural phenomena or something more extraordinary. Dr. Loeb has proposed a systematic approach to evaluating unusual astronomical objects through what he terms the Loeb scale. This framework considers multiple factors, including statistical probability of natural occurrence, deviation from expected physical properties, and consistency with known natural processes. The scale ranks objects from 1 to 10, with higher numbers indicating greater likelihood of artificial origin. Based on current data, 3I/ATLAS has been assigned a preliminary ranking that reflects its multiple anomalous characteristics. However, this score may change as additional observations become available. The scale addresses a fundamental challenge in modern astronomy. How do we objectively evaluate objects that push the boundaries of natural explanation? Traditional scientific methodology excels at studying phenomena that fit established patterns but struggles with truly unprecedented observations. 3I/ATLAS presents exactly this type of challenge. Each individual anomaly might be explained through exotic but natural processes. The unusual size could result from formation around an unusually massive star. The chemical composition might reflect conditions in a protoplanetary disk, unlike our own solar nebula. The precise orbital alignments could represent remarkable but not impossible coincidence. However, when considered collectively, these anomalies create a pattern that strains conventional interpretation. The probability calculations compound, creating scenarios where natural explanations become increasingly unlikely, while alternative possibilities gain credibility. Some researchers argue that we should not dismiss technological interpretations simply because they seem improbable. The universe contains approximately 400 billion stars in our galaxy alone, with trillions of potentially habitable worlds. The mathematical certainty of other intelligent civilizations makes the question not whether they exist, but whether we would recognize their artifacts if we encountered them. Others maintain that extraordinary claims require extraordinary evidence, and that natural explanations, however exotic, should be exhausted before considering artificial origins. This conservative approach has served science well, preventing premature acceptance of sensational claims while ensuring rigorous analysis of unusual phenomena. The debate surrounding 3IATLAS reflects this broader tension within the scientific community. As our observational capabilities expand and we encounter more objects that challenge conventional understanding, these methodological questions become increasingly relevant. As 3I/ATLAS continues toward its appointment with our Sun, it enters a phase that may prove most significant, yet remain largely hidden from human observation. The object will reach perihelion, its closest solar approach, on October 29th, precisely when Earth's position places our planet on the opposite side of the Sun. This timing creates what astronomers call superior conjunction, a period when the object becomes virtually invisible from Earth-based telescopes. Solar glare overwhelms the faint light reflected from 3I/ATLAS, creating an observational blackout that will persist for several weeks during the most critical phase of its solar system passage. The irony is profound. Just when solar heating reaches maximum intensity, and any technological systems would have access to abundant power, our ability to monitor the object reaches its minimum. If 3I/ATLAS were designed to avoid detailed observation during its most active period, this geometry would be optimal. Dr. Loeb has noted that this configuration would allow what he terms a clandestine reverse solar Oberth maneuver. Such a technique would enable a technological object to use the Sun's gravitational field to alter its trajectory while remaining concealed from Earth-based observation. The maneuver could redirect the object toward Earth or other planets, taking advantage of the retrograde orbit that provides access to multiple worlds. During this hidden passage, several spacecraft positioned throughout the inner solar system may encounter evidence of 3I/ATLAS's activity. The Parker Solar Probe, designed to study our Sun's corona, operates in regions where it might detect material released by the object. The European Space Agency's Bepi-Colombo mission to Mercury could provide distant observations from a different vantage point. Most significantly, the Jupiter Icy Moons Explorer, known as JUICE, will observe 3I/ATLAS between November 2nd and 25th as the object emerges from solar conjunction. This spacecraft, currently en route to study Jupiter's largest moons, finds itself perfectly positioned to capture images of the interstellar visitor in its post-perihelion state. These observations may reveal whether 3I/ATLAS emerges unchanged from its solar encounter, or displays modifications that could indicate either natural fragmentation or more extraordinary transformations. The spacecraft's instruments, designed for planetary exploration, will be adapted to study an object that may represent our first detailed encounter with technology from another star system. Despite months of intensive observation and analysis, fundamental questions about 3I/ATLAS remain unresolved. The accumulating data has created a clearer picture of its properties, while simultaneously deepening the mystery of its origins and nature. Radio telescope observations could provide definitive answers about potential artificial signals. Yet remarkably, no major radio facility has been directed toward the object. This represents a significant oversight given the statistical correlation with the 1977 WOW signal and the object's other anomalous characteristics. The scientific community's reluctance to conduct systematic radio observations reflects broader institutional conservatism when confronting phenomena that challenge established paradigms. Dr. Loeb has proposed that radio observatories should target 3I/ATLAS during its remaining passage through our solar system. Such observations would either detect artificial transmissions, providing unprecedented confirmation of extraterrestrial technology, or establish baseline measurements demonstrating the object's radio silence, supporting natural interpretations. The delay in releasing official imagery from the Mars encounter has generated additional questions. Despite the scientific importance of the observations, neither NASA nor the European Space Agency has published the high-resolution images and spectroscopic data collected during the October 3rd flyby. This delay suggests either complex analysis requirements or the discovery of features requiring careful consideration before public disclosure. Government awareness of the situation remains unclear. Following recent interviews about 3I/ATLAS, questions have been raised about whether the United States President has been briefed on the object and its implications. The current government situation has complicated the normal flow of information, leaving uncertainty about official awareness and response preparations. The broader implications extend beyond single object analysis to fundamental questions about our preparedness for contact with non-terrestrial intelligence. Whether 3I/ATLAS represents natural phenomena or something more extraordinary, its study demonstrates gaps in our detection capabilities, analysis protocols, and institutional responses to truly unprecedented discoveries. As we consider the implications of 3I/ATLAS and its passage through our solar system, we must step back and contemplate the broader context of our place in the cosmos. This single object, whether natural or artificial, represents a profound moment in human scientific development. For the first time in our species' history, we possess the technological capability to detect, track, and analyze visitors from other star systems in real time. The international cooperation required for the observation campaigns demonstrates humanity's capacity for coordinated response to phenomena that transcend national boundaries and challenge our fundamental understanding of reality. The methodologies developed for studying 3I/ATLAS will inform future encounters with similar objects and enhance our planetary defense capabilities. Whether these techniques prove useful for analyzing natural comets or something more extraordinary remains to be determined. But the scientific infrastructure created for this investigation represents a permanent advancement in human capability. The questions raised by this interstellar visitor extend, and our species' future development far beyond astronomy into philosophy, sociology. If we are not alone in the universe, how should that knowledge shape our priorities and behaviors? If advanced civilizations exist and occasionally visit our solar system, what responsibilities does that place on humanity? These considerations remind us that science operates not in isolation, but as part of humanity's broader quest to understand our place in a universe that consistently proves more complex and mysterious than our theories predict. Each discovery, whether confirming existing models or challenging fundamental assumptions, contributes to the gradual expansion of human knowledge and wisdom. 3I/ATLAS, regardless of its ultimate nature, has already succeeded in demonstrating that the cosmos holds surprises we have yet to imagine. As it continues its journey past our sun and eventually back into the depths of interstellar space, it carries with it our questions, our hopes, and our growing recognition that we inhabit a universe far stranger and more wonderful than we ever dared believe. The story of this remarkable object serves as a reminder that we live in an age of unprecedented discovery, when the tools of science can peer deeper into space and time than ever before, revealing phenomena that challenge our most basic assumptions about the nature of reality itself. As 3I/ATLAS continues its concealed journey behind our Sun, some researchers have begun exploring theoretical frameworks that venture into truly extraordinary territory. Among the most thought-provoking concepts is what scientists call the dark forest hypothesis, a resolution to the famous Fermi paradox that asks why, in a universe teeming with potentially habitable worlds, we have yet to encounter clear evidence of other civilizations. The hypothesis suggests that advanced civilizations throughout the galaxy remain deliberately hidden, not from cosmic shyness, but from necessity. In this theoretical framework, revealing one's location to the broader galactic community invites potential destruction from competitors for resources or territory. Like hunters moving silently through a dark forest, intelligent species maintain strict communication silence to avoid detection by unknown entities with potentially hostile intentions. Dr. Loeb and his colleagues have noted that if this hypothesis holds merit, then 3I/ATLAS exhibits characteristics that would be consistent with the reconnaissance operations conducted under such constraints. The retrograde orbit aligned precisely with our ecliptic plane would provide what military strategists might term tactical advantages for covert observation. Consider the implications of this orbital geometry. A retrograde trajectory allows access to multiple planetary systems while making long-term tracking and interception extremely challenging for any defending civilization. The object can observe our worlds from various angles and distances while maintaining unpredictable approach vectors that complicate defensive responses. The timing of the solar conjunction adds another layer to this theoretical scenario. An intelligence seeking to study our solar system while avoiding detailed observation would benefit enormously from the natural concealment provided by our Sun's overwhelming glare. During these crucial weeks, 3I/ATLAS receives maximum energy input while remaining effectively invisible to our most sophisticated Earth-based instruments. Some researchers propose that this configuration would enable what they term strategic maneuvers during the hidden passage. The gravitational influence of our Sun could be used to alter trajectories or release smaller objects that might take up positions throughout our solar system, all while remaining undetected by terrestrial observers. However, these scenarios remain purely speculative, representing thought experiments rather than established conclusions. The scientific community continues to emphasize that natural explanations for the object's characteristics deserve thorough exploration before considering more extraordinary possibilities. The question of whether 3I/ATLAS could represent artificial technology has prompted detailed analysis of its observed characteristics against theoretical expectations for interstellar probes. Research teams have examined how an advanced civilization might design objects capable of surviving the harsh environment of interstellar space, while maintaining functionality across potentially millions of years of travel. The engineering challenges for such a mission would be formidable. Any artificial object traveling between star systems would need to withstand cosmic radiation, micrometeorite impacts, and the extreme temperature variations encountered during interstellar flight. These requirements might necessitate protective outer layers composed of materials that could naturally sublimate when exposed to stellar radiation, creating the appearance of conventional cometary outgassing. Dr. Loeb has noted that the absence of non-gravitational acceleration, despite substantial material loss, could indicate either extraordinary mass or sophisticated thrust management systems. An artificial probe might employ controlled outgassing to maintain precise trajectory while appearing to follow purely gravitational motion. Such technology would prevent detection through the trajectory anomalies that typically reveal active propulsion systems. The chemical composition revealed through spectroscopic analysis presents additional considerations. The unusual abundance of nickel and iron could result from protective shielding materials designed to deflect cosmic radiation during long-duration space travel. These elements, while uncommon in natural comets at such temperatures, would be logical choices for spacecraft construction in environments requiring durability and electromagnetic shielding. The massive size of 3I/ATLAS, initially puzzling from a natural formation perspective, becomes more comprehensible when considered as a technological artifact. Advanced civilizations might construct large reconnaissance platforms capable of carrying multiple sensor systems, communication equipment, and possibly smaller subsidiary probes that could be deployed during planetary encounters. However, these technological interpretations face significant challenges when confronted with observational evidence. No artificial signals have been detected from the object, though comprehensive radio monitoring has not been conducted. The outgassing patterns, while unusual, remain consistent with known physical processes involving volatile sublimation under solar heating. Perhaps the most compelling aspect of the 3I/ATLAS mystery lies not in any single anomalous characteristic, but in the convergence of multiple improbable events within a remarkably narrow time frame. When researchers examine the statistical likelihood of these various factors occurring simultaneously by random chance, the mathematics become increasingly challenging to dismiss. The orbital alignment with our ecliptic plane, calculated at roughly 1 chance in 500, represents just the beginning of a cascade of improbabilities. The precise planetary encounters, with combined odds of approximately 1 in 20,000, add another layer of statistical significance. The correlation with the 1977 WOW signal at roughly 1 chance in 200 provides yet another data point in this pattern of convergent anomalies. When probability calculations compound across multiple independent variables, the resulting odds can reach astronomical proportions. Some researchers suggest that the combined probability of all observed characteristics occurring naturally in a single object approaches levels typically reserved for lottery jackpot calculations. This statistical argument has prompted intense debate within the astronomical community about the appropriate interpretation of rare events. Traditional scientific methodology emphasizes that even extremely unlikely occurrences can and do happen naturally, particularly when dealing with cosmic phenomena across vast scales of space and time. Critics of statistical arguments point out that we observe only successful interstellar travelers that manage to reach our detection capabilities. Countless objects may have been ejected from other star systems over billions of years, with only a tiny fraction surviving the journey and achieving visibility from Earth. The apparent improbability of 3I/ATLAS might simply reflect selection bias in our limited sample of detected interstellar visitors. However, supporters of more extraordinary interpretations note that statistical analysis remains a fundamental tool of scientific investigation. When multiple independent measurements all point toward the same unlikely conclusion, the accumulated evidence deserves serious consideration, regardless of how challenging it may be to conventional understanding. As 3I/ATLAS emerges from its hidden solar passage, the global astronomical community has mobilized resources for what may prove to be the most comprehensive study of an interstellar object ever attempted. The European Space Agency's Jupiter Icy Moons Explorer, positioned perfectly for post-perihelion observations, represents just one component of an unprecedented international collaboration. Ground-based observatories across 6 continents have coordinated observation schedules to maximize coverage as the object becomes visible again from Earth. The Atacama Large Millimeter Array in Chile, the Very Large Telescope, and facilities in Hawaii, the Canary Islands, and Australia are all contributing specialized instruments to this coordinated campaign. The observation strategy reflects lessons learned from previous interstellar visitors, where brief visibility periods and limited international coordination resulted in missed opportunities for detailed study. With 3I/ATLAS, researchers have implemented systematic data sharing protocols, ensuring that discoveries made by any participating institution immediately become available to the global scientific community. Advanced spectroscopic techniques will search for chemical signatures that could distinguish between natural and artificial origins. Polarimetry measurements will analyze how light scatters from the object's surface, potentially revealing structural characteristics invisible through conventional imaging. Radio telescopes will finally be directed toward the object, addressing the notable gap in electromagnetic spectrum coverage that has persisted throughout its approach. The intensity of this observational effort reflects both the scientific importance of the discovery and the recognition that opportunities to study interstellar objects remain extraordinarily rare. Unlike periodic comets that return predictably, allowing multiple observation cycles over human timescales, 3I/ATLAS offers a single passage through our solar system before disappearing forever into the cosmic depths. Time constraints add urgency to every observation session. As the object continues outward from the Sun, it will gradually fade from view, eventually becoming too distant and dim for detailed study. The window for comprehensive analysis may span only months before 3I/ATLAS joins its predecessors in the catalogue of briefly glimpsed interstellar visitors. The question of artificial origin has prompted development of new methodologies for distinguishing between natural phenomena and potential technology in astronomical contexts. Researchers have established criteria that any genuinely artificial object might be expected to exhibit, creating frameworks for systematic evaluation of unusual discoveries. These assessment protocols consider factors ranging from structural characteristics to behavioral patterns that would be difficult to explain through natural processes alone. The presence of geometric shapes, controlled trajectory changes, or artificial electromagnetic emissions would provide strong evidence for technological origin, while their absence doesn't necessarily confirm natural formation. 3I/ATLAS presents a complex case study for these emerging methodologies. The object exhibits some characteristics that align with technological expectations, while lacking others that might be considered definitive signatures. This partial correlation creates interpretive challenges that highlight the limitations of current assessment techniques. The absence of clear artificial signals represents perhaps the strongest argument for natural origin. Advanced civilizations capable of interstellar travel would presumably possess sophisticated communication technologies, yet no structured radio emissions have been detected from 3I/ATLAS during its passage through our solar system. However, some researchers note that any civilization conducting covert reconnaissance might deliberately maintain communication silence to avoid detection. The theoretical dark forest scenario suggests that revealing artificial origin could compromise operational security, making radio silence a logical operational requirement rather than evidence against technological nature. The chemical composition presents similar interpretive ambiguities. While the unusual abundance of refractory metals could indicate artificial materials, these same elements might result from formation processes in stellar environments unlike our own solar system. The challenge lies in distinguishing between genuinely anomalous composition and natural variation in interstellar object characteristics. As November progresses and 3I/ATLAS emerges from solar conjunction, the astronomical community prepares for what many consider the most critical phase of the entire encounter. The object's post-perihelion characteristics will provide crucial insights into how it responded to maximum solar heating and whether its fundamental nature remains unchanged. Theoretical models predict several possible outcomes for this emergence phase. A natural comet might display enhanced activity due to volatile activation during peak solar heating, potentially developing spectacular tail structures visible through amateur telescopes. Alternatively, the object might have exhausted much of its volatile content, appearing dimmer and less active than during its approach phase. More extraordinary scenarios consider possibilities that extend beyond conventional cometary behavior. If 3I/ATLAS represents technology rather than natural phenomena, its post-perihelion appearance might reveal modifications indicating controlled systems responding to energy availability during solar approach. The Jupiter Icy Moons Explorer has already begun its observation campaign, capturing images as 3I/ATLAS moves away from the Sun and becomes increasingly visible to distant spacecraft. These initial post-conjunction observations will establish baseline measurements for comparison with pre-perihelion characteristics. Ground-based telescopes are prepared to resume tracking as soon as solar elongation permits safe observation. The transition from spacecraft-based monitoring back to terrestrial observation platforms will require careful coordination to ensure continuous coverage during this critical period. Radio telescope facilities worldwide have finally been scheduled for systematic observation of the object, addressing the notable gap in electromagnetic spectrum coverage that has persisted throughout its solar system passage. These radio surveys will either detect artificial transmissions or establish definitive measurements of the object's radio silence. Regardless of whether 3I/ATLAS ultimately proves to be natural or artificial in origin, its study has already generated profound implications for human civilization and our understanding of our place in the cosmos. The object has demonstrated that our solar system receives visitors from interstellar space more frequently than previously realized, transforming our perception of cosmic isolation. The international cooperation required for comprehensive observation campaigns has created new protocols for coordinating global responses to unprecedented astronomical discoveries. These collaborative frameworks will prove invaluable as improved detection capabilities identify additional interstellar visitors in coming decades. Enhanced observational techniques developed specifically for studying 3I/ATLAS will advance our general capability for characterizing small solar system objects, improving both scientific understanding and planetary defense applications. The methodologies created for distinguishing between natural and artificial phenomena will inform future encounters with objects that challenge conventional categorization. The discovery has also highlighted gaps in our preparedness for truly extraordinary scenarios. The delay in conducting radio observations and the institutional reluctance to consider non-conventional explanations reveal areas where scientific methodology might benefit from greater flexibility when confronting unprecedented phenomena. Educational institutions worldwide have incorporated 3I/ATLAS into curricula as a real-time example of scientific discovery in action. Students can follow observational campaigns, analyze publicly available data, and witness how scientific understanding evolves as new evidence emerges. This educational value extends far beyond astronomy into broader lessons about scientific methodology and critical thinking. As we contemplate the significance of 3I/ATLAS and its passage through our solar system, we must consider the broader context of humanity's relationship with the cosmos. This single object, whether representing natural phenomena or something more extraordinary, marks a pivotal moment in our species' scientific development. For the first time in human history, we possess the technological capability to detect, track, and analyze visitors from other star systems while they actively traverse our cosmic neighborhood. The international cooperation demonstrated during the observation campaigns reveals humanity's capacity for coordinated response to phenomena that transcend national boundaries and challenge fundamental assumptions about reality. The questions raised by this interstellar visitor extend far beyond astronomy into philosophy, ethics, and our species' future development. If we are not alone in the universe, how should that knowledge influence our priorities and behaviors? If advanced civilizations exist and occasionally visit our solar system, what responsibilities does that place on human civilization? These considerations remind us that scientific discovery operates not in isolation, but as part of humanity's broader quest to understand our place in a universe that consistently proves more complex and mysterious than our theories predict. Each discovery, whether confirming existing models or challenging fundamental assumptions, contributes to the gradual expansion of human knowledge and wisdom. The study of 3IATLAS has revealed the remarkable sophistication of modern astronomical capabilities while simultaneously highlighting how much remains unknown about the cosmos beyond our immediate neighbourhood. We can measure the object's size, composition, and trajectory with extraordinary precision, yet fundamental questions about its nature and origins persist. This combination of technological capability and persistent mystery reflects the current state of human cosmic understanding. We have developed instruments sensitive enough to detect individual atoms in the gaseous envelope of an object millions of kilometers away, yet we cannot definitively determine whether that object represents natural phenomena or artificial technology. As 3I/ATLAS continues its journey away from our Sun and eventually back into the depths of interstellar space, it leaves behind more than scientific data and astronomical measurements. This remarkable visitor has fundamentally altered our understanding of what travels between the stars and how frequently our solar system receives such guests. The object carries with it our questions, our theories, and our growing recognition that we inhabit a universe far stranger and more dynamic than previous generations could have imagined. Whether natural or artificial, 3I/ATLAS represents direct physical evidence that the space between stars is not empty void, but an active environment where matter, energy, and possibly even intelligence move across vast distances and timescales. Future interstellar visitors will be met with enhanced detection capabilities, refined analysis techniques, and established protocols for international cooperation. The lessons learned from studying 3I/ATLAS will inform these future encounters, ensuring that humanity is better prepared to extract maximum scientific value from these rare opportunities. The legacy of this investigation extends beyond immediate scientific returns to broader questions about human civilization's readiness for contact with phenomena that challenge our fundamental understanding of reality. The methodologies developed, the international cooperation achieved, and the institutional adaptations made during this encounter will serve as foundation for addressing even more extraordinary discoveries that may await us. As we look toward the stars tonight, we can reflect on the profound realization that somewhere in that vast darkness, 3I/ATLAS continues its ancient journey, carrying within its structure and composition the preserved record of conditions that existed around another star billions of years ago. It serves as a messenger from deep time and distant space, reminding us that our cosmic neighborhood remains full of mysteries waiting to be discovered. The questions it has raised about our place in the universe, the nature of interstellar space, and the possibility of other intelligences among the stars will continue to inspire scientific investigation and philosophical contemplation long after the object itself has faded from our telescopes and returned to the infinite darkness between worlds. In the end, 3I/ATLAS has given us something perhaps more valuable than definitive answers. It has provided us with better questions, deeper mysteries, and an expanded sense of wonder about the cosmos we call home. And in a universe as vast and ancient as ours, That gift of renewed curiosity may prove to be the most precious discovery of all. But perhaps the most intriguing aspect of our investigation into 3I/ATLAS lies not in what we've detected, but in what we haven't. Despite months of intensive study and the object's remarkable characteristics, one crucial element of our analysis remains conspicuously absent from the scientific record. No major radio telescope facility has been systematically directed toward this interstellar visitor. This represents an extraordinary oversight in our comprehensive examination of an object that exhibits such unusual properties. Radio astronomy, the very field that gave us the famous wow signal nearly 5 decades ago, has remained largely silent in its approach to studying what may be the most significant interstellar object ever detected. Dr. Loeb has consistently advocated for radio observations of 3I/ATLAS, noting that such measurements could provide definitive answers about the object's nature. Radio telescopes possess the sensitivity to detect even modest artificial transmissions across interstellar distances, making them ideal instruments for distinguishing between natural phenomena and potential technology. The absence of systematic radio monitoring becomes more puzzling when we consider the statistical correlation with the 1977 wow signal. If 3I/ATLAS was indeed positioned near the origin point of that mysterious transmission, radio observations during its current passage could potentially solve one of astronomy's greatest enigmas. The opportunity to investigate this connection systematically has thus far remained unexplored. Some researchers suggest this hesitation reflects broader institutional conservatism within the scientific community when confronting phenomena that challenge established paradigms. Radio searches for artificial signals carry implications that extend beyond conventional astronomy into questions about extraterrestrial intelligence and humanity's cosmic significance. The technical capabilities certainly exist for comprehensive radio analysis. Facilities like the Very Large Array in New Mexico, the Arecibo Successor projects, and the forthcoming Square Kilometre Array possess the sensitivity and resolution needed to detect structured emissions from 3I/ATLAS if such signals exist. The continued absence of coordinated radio observations represents a missed opportunity that may not recur for decades or centuries. As the object moves away from our Sun and gradually fades from telescopic view, the window for radio detection narrows with each passing week. Future researchers may look back on this period as a crucial moment when the astronomical community possessed the tools to answer fundamental questions about 3I/ATLAS, but lacked the institutional framework to coordinate the necessary observations. An unusual pattern has emerged in the handling of observational data from the Mars encounter that occurred during 3I/ATLAS's closest approach to the red planet. Despite the scientific significance of these observations and the international cooperation that made them possible, several weeks have passed without the expected release of high-resolution images and spectroscopic results. Both NASA and the European Space Agency maintain sophisticated protocols for processing and releasing scientific data from their Mars missions. Under normal circumstances, significant discoveries or unusual observations receive priority treatment, with preliminary results appearing in scientific databases within days or weeks of acquisition. The delay in releasing Mars orbiter data from the October 3rd encounter has generated discussion within the astronomical community about potential complications in the analysis process. High-resolution imaging and spectroscopic measurements of rapidly moving interstellar objects present unique technical challenges that may require extended processing time to ensure accuracy. Some researchers have noted that the complexity of analyzing an object with 3I/ATLAS's unusual characteristics might necessitate additional verification procedures before public release. The unprecedented nature of the observations could require multiple independent analyses to confirm initial findings and ensure that any reported anomalies reflect genuine object properties rather than instrumental artifacts. The European Space Agency has indicated that data processing continues according to established scientific protocols, emphasizing the importance of thorough analysis before drawing conclusions about the object's characteristics. This methodical approach reflects the high standards maintained by space agencies when dealing with potentially significant discoveries. However, the extended timeline has created an information gap during a period when public and scientific interest in 3I/ATLAS remains at peak levels. The Mars encounter represented humanity's best opportunity to obtain detailed close-range observations of the interstellar visitor, making the eventual release of this data crucial for advancing our understanding of the object's true nature. Recent discussions about 3I/ATLAS have raised questions about the level of official government awareness regarding this unprecedented interstellar visitor and its implications. During media interviews about the object's anomalous characteristics, inquiries have been made about whether senior government officials have been briefed on the discovery and its potential significance. The question of governmental awareness becomes particularly relevant given the object's unusual properties and the theoretical scenarios that some researchers have proposed to explain its behavior. Objects displaying characteristics that challenge conventional understanding naturally generate interest from agencies responsible for national security and space situational awareness. Contemporary governmental structures include specialized offices dedicated to monitoring space-based phenomena that could affect national interests. These organizations maintain awareness of potentially significant astronomical discoveries, particularly those involving objects that approach Earth or display unusual characteristics that merit additional investigation. The current political environment has introduced complexities into the normal flow of scientific information between research institutions and government agencies. Administrative transitions and policy reorganizations can affect the timely briefing of officials on emerging scientific developments, potentially creating gaps in awareness about significant discoveries. Some observers have noted that 3IATLAS's retrograde orbital trajectory and precise planetary alignments might attract attention from agencies responsible for assessing potential security implications of unusual space objects. The theoretical scenarios proposed by some researchers, while speculative, involve considerations that extend beyond pure scientific curiosity. However, the intersection between scientific research and government awareness often operates through established channels that prioritize verified findings over preliminary observations. The ongoing analysis of 3I/ATLAS data means that definitive conclusions about the object's nature may not yet be available for official briefing purposes. The question of governmental engagement with unusual astronomical discoveries reflects broader considerations about how society processes and responds to phenomena that challenge established understanding of our cosmic environment. The discovery and study of 3I/ATLAS has revealed important aspects of how modern scientific institutions respond to phenomena that operate at the boundaries of established knowledge. The international collaboration required for comprehensive observation has created new precedents for coordinating global scientific resources when confronting unprecedented discoveries. Traditional academic structures excel at studying phenomena that fit within established theoretical frameworks and observational categories. However, objects like 3I/ATLAS present challenges that span multiple disciplines and require novel approaches to data collection, analysis, and interpretation. The response to this interstellar visitor has demonstrated both the strengths and limitations of contemporary scientific methodology. The rapid mobilization of observational resources, international data sharing agreements, and coordinated analysis efforts reflect the remarkable capability of the global scientific community when focused on significant discoveries. Simultaneously, the investigation has highlighted areas where existing frameworks may benefit from enhanced flexibility when confronting truly extraordinary phenomena. The delayed implementation of radio observations, the extended data processing timelines, and the institutional hesitation to explore certain theoretical possibilities suggest opportunities for methodological refinement. Educational institutions worldwide have recognized the pedagogical value of 3IATLAS as a real-time case study in scientific discovery. Students can observe how scientific understanding evolves as new evidence emerges, witness the importance of international cooperation in addressing global questions, and learn to distinguish between verified observations and speculative interpretations. The development of assessment protocols for evaluating unusual astronomical objects represents another institutional advancement catalyzed by this discovery. The frameworks created for distinguishing between natural and potentially artificial phenomena will inform future encounters with objects that challenge conventional categorization. These institutional adaptations reflect the dynamic nature of scientific methodology, which must continuously evolve to address new types of discoveries and unprecedented observational challenges. The lessons learned from studying 3I/ATLAS will influence how the scientific community approaches similar mysteries in the future. The encounter with 3I/ATLAS has provided valuable insights into humanity's technological readiness for studying interstellar visitors and responding to discoveries that challenge conventional understanding. Our current capabilities represent remarkable achievements, while simultaneously revealing areas where future advancements could enhance our cosmic investigative capacity. Detection systems have proven remarkably effective at identifying and tracking objects of 3I/ATLAS's size and velocity. The ATLAS survey network that discovered the object, combined with follow-up observations from facilities worldwide, demonstrates our ability to monitor the solar system for unusual visitors with impressive precision and coordination. Spectroscopic analysis capabilities have enabled detailed chemical characterization of the object's composition, revealing the unusual abundance of refractory metals and other characteristics that distinguish it from typical solar system objects. These measurements provide direct insight into conditions that existed in another stellar system billions of years ago. High-resolution imaging from space-based platforms like the Hubble Space Telescope has constrained the object's physical dimensions and revealed structural details invisible from ground-based observation. The precision of these measurements reflects decades of advancement in space-based astronomical instrumentation. However, the investigation has also identified areas where enhanced capabilities could significantly improve our understanding of similar future discoveries. The absence of systematic radio monitoring represents a notable gap in electromagnetic spectrum coverage that could be addressed through coordinated observation protocols. Rapid response capabilities for newly discovered interstellar objects could benefit from enhanced international coordination mechanisms that enable immediate deployment of appropriate observational resources. The brief visibility periods of these visitors make rapid mobilization crucial for maximizing scientific return. Spacecraft positioned throughout the solar system have provided unique observational opportunities during periods when Earth-based telescopes face geometric limitations. The Mars orbiter observations and forthcoming Jupiter system observations demonstrate the value of distributed observational platforms for comprehensive object characterization. As we reflect on the journey of discovery that 3I/ATLAS has provided, we must consider the broader philosophical implications of encountering phenomena that challenge our fundamental assumptions about the nature of cosmic reality. This single object, regardless of its ultimate classification, has prompted questions that extend far beyond astronomical curiosity. The statistical improbabilities surrounding the object's characteristics and trajectory have forced researchers to confront uncomfortable questions about the role of chance versus intention in cosmic phenomena. When multiple independent measurements all point towards scenarios that strain natural explanation, we must examine our methodological assumptions about how to interpret such convergent anomalies. Some philosophers of science suggest that our current frameworks for evaluating unusual discoveries may be inadequately prepared for encounters with genuinely unprecedented phenomena. The methodologies that serve us well for studying familiar objects within established categories may prove insufficient when confronting visitors from other stellar systems. The possibility that we might be sharing the galaxy with other intelligent civilizations raises profound questions about humanity's cosmic significance and our responsibilities as participants in a potentially populated universe. If advanced technologies traverse the space between stars, what ethical considerations should guide our response to such discoveries? These philosophical dimensions remind us that scientific discovery operates within broader contexts of human meaning-making and value formation. The technical measurements and statistical analyses that define our study of 3I/ATLAS exist alongside fundamental questions about consciousness, intelligence, and our species' place in the cosmic order. The international cooperation required for comprehensive study of this interstellar visitor demonstrates humanity's capacity for transcending terrestrial divisions when confronting questions of cosmic significance. This collaborative response suggests positive possibilities for how our species might address future discoveries that challenge established understanding. Educational institutions have recognized the value of 3I/ATLAS as a case study not only in astronomical methodology, but in critical thinking, international cooperation, and the dynamic nature of scientific knowledge. These broader educational applications extend the object's impact far beyond specialized research communities. In the quiet hours when Earth turns away from the sun and the stellar dome reveals itself in all its ancient glory, we can contemplate the profound journey that 3I/ATLAS represents. Somewhere in that vast darkness, this remarkable visitor continues its eternal voyage, carrying within its structure the preserved record of processes that occurred around another star when our own solar system was young. The object serves as a physical messenger from deep time and distant space, connecting us directly to stellar environments that may no longer exist. The elements within its composition were forged in nuclear furnaces that blazed across the galaxy billions of years before Earth formed, dispersed through space by stellar explosions that seeded the cosmos with the building blocks of worlds. Its journey through interstellar space spans temporal scales that dwarf human civilization. While our species developed language, agriculture, and technology, 3I/ATLAS travelled silently through the cosmic void, preserving chemical signatures from its origin system like a geological sample from another world. The mathematical precision of its trajectory through our solar system, whether representing remarkable coincidence or something more intentional, reminds us that we inhabit a universe where the boundaries between the probable and the impossible remain fluid and mysterious. Each measurement we've obtained raises new questions about the nature of cosmic reality. The international scientific collaboration that this visitor inspired demonstrates humanity's capacity for unity when confronting mysteries that transcend terrestrial concerns. Researchers from dozens of nations contributed observations and analysis, creating a global network of inquiry focused on understanding a single cosmic phenomenon. As 3I/ATLAS continues outward toward the edge of our solar system and eventual return to interstellar space, it carries with it our questions, our theories, and our growing awareness that the universe holds surprises we have yet to imagine. The brief intersection of its ancient journey with our moment of technological capability represents a fleeting opportunity to glimpse processes and possibilities that operate on scales beyond everyday human experience. The story of 3I/ATLAS extends far beyond its current passage through our solar system into questions that may define the future of human cosmic understanding. As our detection capabilities improve and additional interstellar visitors are discovered, the methodologies developed for studying this remarkable object will inform countless future investigations. The Vera Rubin Observatory and similar next-generation survey systems promise to revolutionize our awareness of the interstellar object population. What currently appears as rare cosmic curiosities may prove to be common travelers in the space between stars, each carrying unique information about stellar systems throughout the galaxy. Enhanced spectroscopic techniques will enable more detailed chemical analysis of future visitors, potentially revealing the diversity of planetary formation processes across different stellar environments. The unusual composition of 3I/ATLAS may represent just one example of the chemical variety that exists among worlds orbiting other stars. Radio astronomy capabilities continue advancing towards sensitivity levels that could detect artificial signals across interstellar distances with unprecedented clarity. Future interstellar objects will be subject to comprehensive electromagnetic spectrum analysis, ensuring that potential technological signatures receive appropriate investigation. Space-based observational platforms positioned throughout the solar system will provide multiple vantage points for studying future visitors, eliminating the geometric limitations that constrain some aspects of 3I/ATLAS observation. These distributed capabilities will enable continuous monitoring regardless of solar conjunction periods. International cooperation protocols developed for this investigation will serve as templates for coordinating global responses to future discoveries that challenge established understanding. The collaborative frameworks created for studying 3I/ATLAS represent permanent advances in humanity's capacity for addressing cosmic mysteries. The questions raised by this interstellar visitor about artificial versus natural phenomena will continue inspiring development of more sophisticated assessment methodologies. Future encounters with unusual objects will benefit from refined criteria for evaluating potential technological signatures while maintaining rigorous scientific standards. Perhaps most significantly, the sense of cosmic wonder and expanded awareness that 3I/ATLAS has generated will influence how future generations approach questions about humanity's place in the universe. This single object has reminded us that we live in a cosmos filled with ancient travelers carrying messages from distant worlds, and that our growing technological capabilities provide unprecedented opportunities to read those messages and understand their implications. As we look toward the stars tonight, we can reflect on the profound realization that the space between worlds is not empty void, but an active environment where matter, energy, and possibly intelligence move across vast distances and timescales. The journey of 3I/ATLAS through our solar system represents just one moment in this vast cosmic circulation, but it has opened our eyes to processes and possibilities that will inspire scientific investigation and philosophical contemplation for generations to come. In the end, this remarkable visitor has given us something more valuable than definitive answers. It has provided us with better questions, deeper mysteries, and an expanded sense of wonder about the infinite cosmos we call home. And in a universe as vast and ancient as ours, that gift of renewed curiosity and cosmic perspective may prove to be the most precious discovery of all. The lights in the sky continue their ancient dance, and somewhere among them 3I/ATLAS continues its eternal journey, carrying our questions into the infinite darkness between worlds, reminding us that we are part of something far greater and more mysterious than we ever dared imagine. But as we stand at this crossroads of cosmic discovery, new questions emerge that challenge our most fundamental assumptions about what we're witnessing. The story of 3I/ATLAS has evolved beyond a simple astronomical observation into something that touches the very core of how we understand our place in the universe. Recent analysis has begun revealing patterns within patterns, connections that reach across decades of scientific observation and into the deepest mysteries of our cosmic neighborhood. What started as the study of a single interstellar visitor has become a window into processes and possibilities that operate on scales we're only beginning to comprehend. The accumulated data from months of observation campaigns has created a comprehensive portrait of an object that consistently defies easy categorization. Each measurement, each spectroscopic analysis, each trajectory calculation adds another piece to a puzzle that grows more intriguing rather than more clear with each addition. Research teams worldwide have begun collaborating in unprecedented ways, sharing not just observational data but theoretical frameworks that push the boundaries of conventional astronomical interpretation. The methodologies developed specifically for studying 3I/ATLAS are already being applied to other unusual objects in our cosmic catalogue, revealing that this visitor may not be as unique as initially believed. Some astronomers suggest we may be witnessing the early stages of a fundamental shift in how we perceive interstellar space itself. Rather than the empty void between stars that previous generations imagined, we're discovering an active environment where objects, materials, and perhaps even information travel regularly between stellar systems. The technological capabilities that enabled our comprehensive study of 3I/ATLAS represent just the beginning of a new era in cosmic awareness. Advanced survey systems coming online over the next decade promise to revolutionize our understanding of what travels through our solar system and how frequently such encounters occur. The Vera Rubin Observatory's remarkable performance during its initial operations has already transformed expectations about interstellar object detection rates. The facility's ability to identify over 2,000 new objects in just 10 hours of observation suggests that our previous estimates of cosmic traffic may have been dramatically conservative. Next-generation radio telescope arrays, under development, will provide sensitivity levels capable of detecting structured signals across interstellar distances with unprecedented clarity. These systems will ensure that future interstellar visitors receive comprehensive electromagnetic spectrum analysis, addressing the notable gap that has characterized our study of 3I/ATLAS. Space-based infrared observatories, scheduled for launch in the coming years, will operate beyond Earth's atmospheric limitations, providing continuous monitoring capabilities regardless of solar conjunction periods or seasonal observing constraints. These platforms will enable extended observation campaigns that span the entire passage of interstellar visitors through our solar system. International space agencies are developing rapid response protocols specifically designed for newly discovered interstellar objects. These frameworks will enable immediate deployment of observational resources, ensuring that future visitors receive comprehensive study throughout their brief visibility periods. The coordination mechanisms established for studying 3I/ATLAS have created permanent improvements in how the global scientific community responds to unprecedented discoveries. Data sharing agreements, observation scheduling protocols, and analysis methodologies developed during this investigation will serve as templates for addressing similar mysteries in the future. Enhanced spectroscopic techniques continue advancing towards sensitivity levels that will enable detailed chemical characterization of much smaller and more distant objects. Future interstellar visitors will be subject to analysis that reveals their compositional secrets with precision that was unimaginable just decades ago. As our understanding of 3I/ATLAS deepens, we begin to glimpse the broader context of galactic processes that operate on scales spanning millions of years and countless star systems. This single object represents just one data point in a vast network of material exchange that connects stellar systems throughout our galaxy. The story of 3I/ATLAS reminds us that we live in a universe far more connected and mysterious than we ever imagined. This ancient traveller from another star has shown us that the space between worlds is not empty void, but an active realm where matter, energy, and perhaps even intelligence flow across unimaginable distances. As it continues its eternal journey back into the cosmic dark, 3I/ATLAS carries with it our questions about what else might be travelling silently through the galaxy. And perhaps most remarkably, it has given us the gift of wonder itself, expanding our perspective and reminding us that in this vast cosmos, the greatest discoveries may still await us among the stars.